Okay. So how is everyone doing? Good. So today is our last class, and I appreciate you all attending classes and listening to the lectures. I hope this class has been useful. Practically, I probably needed one or two more classes to kind of cover everything that I wanted to cover. Like I missed one class in the beginning, and then I think we had one less class for holidays. But I think I've like covered enough like foundational material so that you can pick up some of the additional topics, and I'll try to mention some like what can you learn next, and what I haven't covered that is useful, and there are some, like for example, I haven't touched generative modeling at all. So generative AI is a big thing, right? So deep generative models. So I'll try to give you some pointers to some resources so that you can take a look at that. Right. What's that sound? Is it from the Zoom?
No, that was there yesterday or
Okay.
Monday as well. It might be the speaker, it might be.
Are you able to mute? Can you mute on here?
Yeah, it's that speaker.
Okay. I mean, I'm recording, so.
Or just like this, turn off the sound?
Oh, here?
Yeah.
This one?
Yeah, maybe.
That work?
No?
Is there like a system, doesn't that desk have like controls for the?
So yeah, it's because it's output, or it's something related to outputting audio.
Yeah, I'm not gonna figure it out. Like, we'll have to live with it. But we also need to record it because someone cannot make it. So let's hope it works out.
It was doing that on Monday.
Yeah, it was. Yeah, I remember. So where are we? So I should kind of recall where we are. So we mentioned that like neural networks or deep learning has these three big puzzles, right? Like one is the three big questions, right? Approximation. Can we approximate any arbitrary function, whether it's continuous or discrete, right? And we learned that that's true, right? And then we talked about learning and optimization. We talked about several methods like stochastic gradient descent, ADAM, and like we covered this, but there is a lot of open questions here in terms of like what are the best learning algorithms, or what are the best ways to optimize the loss function. So there is still a lot of research going on here. Like we talked about ADAM, but now everyone is crazy about some new algorithms like muon, right? It's a new kid in the block, and everyone uses muon now. So we haven't covered that, but I believe someone in the class is doing a project on it, so maybe we'll hear about that in the course projects. But the foundation that we've covered here would allow you to kind of pick up some of these new training methods and kind of understand or apply them in your projects, right? Or try to see what are the drawbacks of these methods and try to do your own improvements here, right? So that's kind of a bit more on the research side, but you can also like apply these algorithms to your applied projects, right? And then we talked about generalization, right? And we talked about classical generalization. And then we also talked about like in modern neural networks, we have a lot, like an extremely large number of parameters, and still even if you're fully memorizing the training data, we are still able to generalize, right? And we saw one phenomena of double descent, where the test error kind of increases and then suddenly it goes down again, right? Which means that it doesn't hurt to kind of add more and more parameters to your network, right? And that's why we are spending billions of dollars in data centers. All the big players are just investing more and more resources to kind of add more parameters to their model. Every time there is a new GPT update, the main change is that there are more parameters, right? The model is larger. And then that's just kind of the scaling approach where, in fact, for a lot of these models right now, there isn't much innovation happening. All we have to do is like throw in more money, add more layers, more neurons, more special blocks. Just the same thing, just do it more. And that seems to work to improve the performance of the models, right? Ilya Sutskever, who's kind of one of the founders of OpenAI, he thinks that we've reached the limit of how much we can just scratch out of these models by just scaling that way. So he thinks we need to go back to the blackboard and kind of start new research. But we'll see. Like the large organizations are still just increasing the capacity of the models just because of the double descent phenomena, where there is an initial peak where the test error goes up, but again it keeps going down again. So we can drag it down almost to zero. Okay. And then, so like this kind of gives us a good foundation for neural networks and deep learning. And then we started to talk about these like custom architectures, right? Like we started talking about the CNN architecture, right? And like today we'll kind of try to cover the transformer and possibly a bit of the RNN architecture. But what's common in all these architectures is the notion of inductive bias, right? The inductive bias means that in our architectures, if we can embed some domain knowledge, then we can make learning more efficient. We can learn with less data, right? The example for images is that any image is typically translation invariant, right? If you have a picture of an animal on the upper left corner of your image, if you move it down and on the right, and you try to do a prediction, you will have the same object, right? So that's known as invariance. Invariance means that if you have an image like this, right, something like that, and then you do some sort of transformation of that image where you translate it horizontally, and then your image is right here, and then if you do a prediction here, you get the same answer, right? So maybe this is like a dog. I meant to draw a dog, right? Mathematically, we can say that, so let's say f is my function or neural network. I have an image I, and I apply the function to get a prediction. That's the same as first doing translation on the image and then doing the prediction, okay? So that's the mathematical way of writing this invariance. And what we are doing with the CNN filters is basically we are encoding this type of invariance into the model. And what is the benefit of that? The benefit of that is that you get quite a bit of sample efficiency or data efficiency, right? Because if you have that upper left image in your data set, you don't need to provide another data set where your image is shifted or pushed somewhere else, because the model itself knows that any translation is also, any translation of that image is also like the same object. So we have kind of given that knowledge even before we start training with our data to the model. So we don't need to provide additional data. So if we did not have the CNN filters, and if you wanted to use just vanilla multi-layer perceptron, then we would have to provide these additional data points where we have the original image and the translated image. We have to give all those data, right? So there is data efficiency, and there is also parameter sharing, right? So like the advantages of this type of this invariance, what this buys us is data efficiency, and parameter sharing, right? Because the filter is a small part compared to the original image. The filter is a small number of parameters, and you're sharing that across all your patches, right? So if you recall, we had if you have an image like this, right? Then we were breaking up this into like these patches, which can be overlapping. And then we have a filter which runs through all of these patches. But the filter has these weight parameters, right? The filter is basically a bunch of numbers, and those are all unknown numbers which we are learning in the network, right? But that same patch of filter is applied across the network, across the image. So we don't need like if this image is like, for example, 1 million pixels, we don't need 1 million square parameters anymore. Based on what is the size of the filter, like let's say compared to your image, this is like a 1000 by 1000 filter, then that's all the parameters you need. You don't need 10 to the power 12 parameters, you need just 10 to the 6 parameters. So there are a lot of saving here because this same filter is applied across all the patches, right? So the motivation of like something like CNN is that these filters kind of, at least at the early stage of your network, they're trying to figure out like simple patterns, right? You might have a filter to identify a vertical edge or a horizontal edge, right? So your initial layers of your CNN are going to be for these low-level features, and then as you add more layers, you kind of start to recognize higher level features, and then eventually at one point you kind of see that your image is actually you're able to kind of detect the actual image or the object in your network, right? So it's this is also called hierarchical representation, and this is motivated by how the human visual cortex works. The experiments tell us that the human visual cortex identifies images in a hierarchical manner. Like our initial layers understand like low-level features like horizontal edges, vertical edges, or like a circle, and then as you move beyond like the initial layers, you kind of start to kind of assemble more complex patterns, right? So we kind of looked at examples of filter computations, right? And I'm not going to go through it again. But one way to kind of understand kind of the CNN, the filter mechanism, what we are what we are, you can think of every patch in the image. Let's say it has like a center pixel. Okay, think of it having a center pixel, right? And we are just trying to find a representative value or representation of that center filter, and that's what the filter does. Center, every patch has a center pixel, and we are just looking at the neighbors of any neighboring pixels of that center pixel, and trying to find a weighted combination of all its neighbors, and using that to find a value for that pixel, right? So we get those weights by and the weights are provided by the filter object, right? The filter is a set of numbers, and those numbers tell us what the weight is, right? So like for example, let's say let's just draw up just some numbers. Right, let's say this is kind of an up top part of a filter. We have these two patches. Okay, and then let's say, so this is my image, and let's say I have a filter which is like this. Right? So I would initially take this filter and kind of map it onto this part, and then we know the operation is basically we multiply the corresponding quantities and add them up, right? So you can think of this as what we're doing here. The value in this object in this patch is going to be like 1 times 1 plus 1 times 2 plus minus 1 times 3 plus 2 times 4 plus dot dot, and finally it's going to be 3 times 9, right? So you can think of, you are taking, so now consider that you have this center pixel 7 here, right? So 7 itself has a weight here, right? The weight of 7 is 1, but then every other pixel in its immediate neighborhood, like these are one-hop neighbors, like vertically, horizontally, or diagonally. For each of them, you kind of add their neighboring pixel contributions and add a weight, and the weight comes from the filter. So this combination that you're doing here is kind of like a weighted average of the pixel values of all immediate neighbors, right? That's another interpretation of how the CNN filter computation works. Okay, and then if we think about that, now let's say like somehow as a simplification, we have like we are just considering a 1D image, right? It doesn't make sense, but mathematically we can think about it that way. So let's say my image has these pixels x1, x2, x3, x4, x5, x6, x7. Okay. Just as an example to kind of understand the computation, I think of this as my image where I have kind of 7 rows and just 1 column, right? I'm just kind of telling you a simplified example. But if you now think of what we just said, that we have these patches where every patch has a center, and we are computing the weighted average of all the neighboring pixels. So if you apply the same idea to this object, let's say in this case we are going to consider every pixel, like in this case x1, and then just look at its previous neighbor and the next neighbor, right? So for x1, right, x1 has a previous neighbor. It doesn't have previous neighbor because it's the first one, but x1, let's say, is by itself one value, so I'm going to say it's going to be bx1 plus the next neighbor is x2, which is cx2. Okay, so this is going to be my weighted average of the pixel's own value and its neighbors. In this case, it's simply it only has, every element can have at most two neighbors, the one before it and the one after it, right? So this is a simplified example. So if I apply a filter, so my filter is going to have three numbers, A, B, and C, right? So this is the kind of the previous pixel, this is the current pixel, and this is the next pixel. That's going to be my filter. And now if I apply the filter at this position, then what value will I get? Can anyone tell me? I'm going to take this, basically I'm taking this 3-number filter and I'm placing it. So this is my current patch of the image, and I have A, B, and C here, and then I'm going to compute the filter value. So what value will I get? Just from the 2D example, just think of a 1D vector example. This is like again a patch in a vertical image, and I'm multiplying by this filter. So I'm just going to multiply the corresponding, yeah, go ahead.
AX2 plus BX3 plus
Yes, exactly.
CX4.
Right. So AX2 plus BX3 plus CX4, right? And then if I then shift it down again once, so here this is X3 is the center pixel in this patch. My next patch is going to be like this one, right? X3, X4, and X5. In that case, X4 is the middle patch, and then this would be AX3 plus BX4 plus CX5. And then the next patch is going to be AX4 plus BX5 plus CX6. And then the last patch is going to be, the next patch is going to be for 6 is going to be AX5 plus BX6 plus CX7, right? And then finally we have a corner patch where we just have a previous one. So that is going to be X. What will be the last patch? For the last patch, we have X7 as the, X7 is the current value. So that will get the middle point B. So it will be B X7, and the previous one is going to be A X6, right? So that those are the borders. The borders always have less values, right? So this is my computation, right? So what we got here is, so basically you can see that these values that I get, I have a 7 pixels in my input 1D image, and I get 7 output pixel values. So it is a linear transformation. So if it's a linear transformation, right, we agree this is a linear transformation, right? There are no quadratic terms or anything. So that means there is a matrix that represents that if I multiply the matrix by this vector, I should get this output vector, right? So we can try to identify that, right? So what would that matrix look like? So it's going to be some matrix, and it's going to be multiplied by x1, x2, x3, x4, x5, x6, x7, right? If you look here, the first element is bx1 plus cx2, right? So then we have b here and c here, and everything else should be 0, right? Because there are no other contributions. For the next one, it's ax2 plus bx3 plus cx4. So 2, 3, 4, these would get coefficients a, b, and c, and everything else gets 0 coefficient. So we just shift our pattern to the right by once, and we should get it's going to be x2. So there is a one missing here, right? This was for x3, so I should have ax1 plus bx2 plus cx3. So that is going to be a, b, c, everything 0, right? And the next one is going to be basically every time you have a new row, you're going to shift this pattern to the right, right? So next one is going to be a, 0, a, b, c, 0, then 0, 0, a, b, c, 0, 0, 0, 0, a, b, c, 0, and so on, right? Okay. So we should be able to fill this out. But this, if you look at this matrix, it has a special property, right? It has a whole bunch of zeros, very sparse matrix. Across the diagonal, you have all b's, which is the coefficient that goes with the center pixel. And then you have a array of a's below the main diagonal and an array of c's out of the main diagonal. And there is nothing else. Everything else is 0. So that means our filter operation is basically a special matrix multiplication. Nothing else, right? So that means that it's almost like just a linear perceptron, right? In a linear, if you have a linear multilinear perceptron layer, you take your input activation vector and multiply by matrix, and you get your output activations. So the CNN is nothing other than it's similar. It's almost a special case of a general neural network multi-layer perceptron layer, but it has just as a special structure where you have a lot of zeros and you have much less parameters, right? So you have only, in this case, only 3 parameters. Whereas if this was a full MLP layer, you would have like d by d different parameters. Okay. So what this tells us that is first of all, we have a lot of parameter sharing, and we have to learn a much less kind of sparser weight matrix here. We just have to learn, in this case, 3 parameters. So it's much easier to learn here, right? So what this tells us is that, and this holds also for the 2D case or 3D case of an image, right? They're all the same cases. So the kind of the CNN filter or the convolution is just a special matrix multiplication operation, right? Which means when we are thinking about training and backprop, we just think of it as a matrix as a sparse matrix with much less parameters. But otherwise, all this stuff like backpropagation works as before, right? So we don't have to invent any new type of training for the CNN. The training is basically the same as before. Okay? And the reason I'm saying this is that means my filter operation is basically, I have a output vector y, which is just a matrix and the input image, right? And so that's my basically where W is a sparse matrix, right? And the reason I'm mentioning this is that I want to argue that we don't need a new type of like differential operator to do backpropagation here, because it's just a matrix multiplication. And we know how to take the Jacobian or derivative of the matrix multiplication, right? So that means that in our backpropagation, we don't need to, we can just think of this as a matrix operator. And we know how to do backpropagation with matrix operator. Okay? The other thing that we saw in the CNN is the max pooling operator. Right, what is max pooling? Basically, if you have a small patch like this, all we do is basically find the maximum value in this patch and output that as the value. So this is going to be like the max pool is just going to be the simple 1 pixel 8, right? So we do this when we do this in our network. We are basically downsampling the image, right? And this also has kind of a smoothing effect. We are kind of smoothing out the variations, and this kind of helps the network generalize and learn a bit better, right? So with this in mind, what we have in the CNN architecture is these are the main operators that we have in CNN. So we have like a convolution layer. So that's the convolution that we do, plus a nonlinearity, which is like ReLU. And then we have a max pool operator, okay? And that gives us one convolutional block, right? So we apply this convolutional block on our images and we get an output, a kind of a possibly downsampled image with less resolution, right? So if I can call this like this is one convolutional block, right? And then what would happen is that in your image, you're going to apply the image and you're going to take one convolutional block, right? And this will typically be a filter bank, right? We will have multiple filters that represent different types of image sub-features that we are trying to kind of recognize. And then this gives you like a tensor output, right? And then you keep doing this, right? Let's call this convolutional block. We pass it through another convolutional block and another one, right? And then finally we might have a softmax at the end. And then I have my output, right? So that's your general convolutional architecture. We build these convolutional blocks which has a number of convolutional filters followed by a nonlinear equation like ReLU and then a max pool, right? And we just kind of compose this together as much as we want, and then we have a CNN architecture. And this is kind of the general architecture of all the popular CNN architectures like AlexNet. And there is VCGNet. There is like things like ResNet. These are some of the well-known CNN architectures. They all have this common structure. Okay.
I have a question.
Yeah.
When does backpropagation, like, does it have difference? Because then does it backpropagate through the convolutional blocks, or does it only backpropagate the
Backpropagation is exactly as before.
Okay.
When you do backpropagation, you can think of this. You can think of this as just a general MLP and do backprop.
Okay.
The only thing that we need to know is the max pooling operator. How do you differentiate that, right? But that's also easy, right? Because max pool is just a max operator, right? So if you do, what is max pool doing? You have a bunch of numbers, you take the max of it, right? So we argued that the convolution is just a special matrix. So in backprop, you just do the derivative of the matrix, and you have the solution, right? So that's already done. Nothing new there. It's just a simpler matrix. The only new element is a max pool, which is the max of x1, let's say x2, right? As a simple example. I mean, this is just like it's going to be x1 if x1 greater or equal to x2 and x2 otherwise, right? And then if you take the gradient of this, what would be the value? To find the gradient is basically you just do case wise, right? So first case is x1 greater or equal to x2, right? In this the max value is x1, and then the gradient of x1 with respect to grad with respect to so you're gonna do this basically you're kind of finding the derivative with respect to either parameter, right? So this will be like del by del x1, right? So this is going to be 1 and 0 otherwise. If x2 is greater, then it's going to be 0, and the other case is exactly the opposite, right? So then the derivative here you can express as this is going to be the delta function that the condition x1 is greater or equal to x2, and then with respect to del of x2 it's going to be just the opposite example, like x1 is less than x2. Okay, so that gives you the derivative, and this is very similar to the ReLU derivative, right? So once you have this derivative in your object, when you actually implement this, your max pool is going to be like an operator node in your computational graph, right? And you just your node Jacobian is this, and then you do backprop where you kind of receive an upstream gradient, and you multiply that with your Maxwell gradient, and you send it downstream. It's exactly the same operation. Okay, so backprop is nothing new for CNN architecture. So the other thing to remember is that your image might have multiple color channels, right? But that's basically not a problem, right? If you have 3 channels RGB, your image looks like this, right? So you have three channels, like this is R, G, and B. And then how do you deal with this multi-channel input image? So now this is like a cubic object, right? Yeah. So your filters will also be small cubes. Right? So your filter dimension also increases by 3. Right? So basically, if this is like, for example, 128 by 128, then this tensor is 3 times 128 by 128, and then your filter might be the first dimension filter must match the number of channels, so it should be 3, and you can do like 3 by 4 by 4, right? Then that's gonna like run through all your cubic batches now, and then you decide. Yeah, go ahead.
When the CNN is learning, do the filters get adjusted, or do they always stay the same?
Oh, the filters get adjusted. The filter, what is a filter here? This, when I say this filter is 3 by 4 by 4, it's a tensor of 3 by 4 by 4 numbers. So 48 numbers. You start them by, again, randomly assigning these numbers. You might use some sort of initialization, just like we saw last class. Just use some random numbers, sample from a normal distribution with small variance. You initialize with that. But then when you are running through and in the forward passing, you get the loss, right? Then you backpropagate the gradients. But the gradients are with respect to the parameters in the filter, right? And those numbers, that filter is like a matrix object. You take the derivative, then your gradient is going to be with respect to those filter weight objects, and then you use gradient descent to adjust those weight values. Every parameter, you have a gradient descent for that parameter, right? And one thing that I should show here is that before the softmax, there is typically a fully connected block. Or before we actually, once we run through these convolutional blocks, we always end with a fully connected layer of network of neurons, just like a simple MLP. That's kind of the basic architecture, right? Kind of the rationale for that is that in general with the convolutional blocks we save a lot of parameters. Like we don't need lots of parameters. But if you're saving too much, maybe we don't have enough complexity. So at the end you kind of rush in some additional parameters so that your model is complex enough, right? So that's kind of a rationale for having the fully connected layer at the end. Okay, and this is common in all these architectures like AlexNet. So AlexNet was from the University of Toronto. It was the first CNN model that actually like beat all the other benchmarks in the ImageNet competition, and that kind of started the revolution of deep learning, the revolution around 2016. After that, like people did a lot more improvements on this and kind of were able to kind of surpass human level performance on these objects, on these tasks. But that was a big breakthrough, the AlexNet. And then the funny thing is that like after AlexNet came out from academia, all the industry labs like Microsoft Research, Google Labs, they all kind of started to come up with their own architecture. But all they were doing is this basically, most of them were just kind of just scaling it, or kind of adding more and more layers. So they had a lot of money and a lot of compute. They just added more and more these convolutional blocks or more fully connected blocks to kind of get better performance. That was the main game, right? And then in ResNet had something interesting, and we'll talk about that. ResNet kind of stands for residual connections. So I'll mention that in a bit. That was a new idea. That was a very powerful idea. So let's look at a bit at the ResNet architecture. What ResNet did is basically you have an image, right? And then you pass it through a convolution block, right? Another convolutional block, another one, and then a fully connected layer, and then you have your output. Okay. So this, like, you can think of this in the full architecture, there is like maybe 100 layers here. I'm just drawing 3 layers, but there will be hundreds of layers here. But what ResNet did is that, so tell me something, like if I design such an architecture, right, how do I decide how many convolutional block layers I'm going to have in my network? Like how would you kind of think about the best number of layers that you want? Like more is better usually, but not always. So you have to probably experiment with it, right? So maybe you try with 1 block, maybe try with 5 blocks, 10 blocks. Just it's like randomly trying out all possible. So the number of layers is like number of blocks is like a hyperparameter in your model. Yeah, until it doesn't overfit or something like that, right? So you have to kind of play this game of checking overfitting and then maybe reducing the number of blocks. But the very interesting idea in ResNet is that ResNet added these like bypass connections, right? So it kind of says that, okay, I might just skip one of these blocks and do an identity transformation here, or kind of do a skip connection here, right? And the impact of this connection is that sometimes your forward pass goes through all of the layers, and sometimes it's skipping some connections, right? And when you skip some connection, it's almost like you're reducing the number of blocks here. And whether you're going to use a skip connection or not is also a parameter in your ResNet architecture. So you're kind of letting the network learn at a meta level what is the best number of convolutional blocks that would help it. So it's a simple but like very powerful idea. You're letting your network architecture add up by itself. Before these ideas like ResNet, you would have to beforehand fix how many blocks you want, right, in your network. Now I might just say I'm going to use like 1,000 blocks and then add these skip connections, and I let the network decide what is the optimal number of blocks that you want, right? So that was a big thing by ResNet, and it was from Microsoft Research. And this was actually a very successful architecture for object recognition and computer vision. Okay, so that's all I will cover for CNN. Next, we're going to talk about RNN and transformer architecture. RNN is very briefly, but I will try to spend a bit more time on transformers. And the reason is transformers, as you know, right now is the big thing, right? Like if you go to an interview, they're going to ask you about transformer. They're going to ask you what is flash attention, what is self attention, right? So, like. And what we'll try to understand is that the attention architecture is a universal architecture. And there is a misconception here in that we all think that attention is only useful for language modeling or LLMs. But attention is also useful for vision tasks or any other model. It's a generalized architecture that works for all possible models. And right now it's the race. And everyone is using transformer. Any problem that you have, we always throw in a transformer, and it usually works pretty well, right? So we'll try to look at it in the remainder of the class today. We'll try to look at the transformer architecture. Okay, so I think this is a good time to have a short break. So let's reconvene at 9 p.m. Let's take an 8-minute break.
About the reverb on that speaker? No.
So we've discussed the CNN architecture. So we have these like preconceived notions in our mind, right? Whenever, like in general, whenever we see an image, we know that, okay, CNN is going to be a good fit for us, right? Like it should be very good for us if I choose a CNN architecture, right? So images, like we kind of always think that the best architecture is a CNN or some variation of it, right? And then if you have a sequence or a series, then the architecture that we usually associate with that is a recurrent neural network, right? So whenever you have a sequence of data and you want to learn, like you want to predict something over time, right? So an example is that like a stock market, right? You want to, what you have is you have temporal data of stock prices over like 5 years or something, and you want to predict what is going to be the stock price going to look like in the immediate future, so that you can buy or sell. Of course, the financial data is, we know there is a lot of theory that says that financial data is very hard to predict with low variance, right? I think some of you are working on that project, but it could also be like temperature, right? You have a time series of temperature, you want to predict the next temperature. So that's a sequence problem, right? What you have, you can have a sequence of values, right? So it could be like your sequence, let's say some number x1, x2, up to xn, right? That might be the data that you have. And then you want to predict what's maybe xn plus 1, the next value in the sequence, right? You have temperature data for a city up to the current time, and then you want to predict the next week, what is the temperature going to look like for the next 7 days, right? So that's a sequence problem or time series problem. And that's where kind of this recurrent architecture comes up, right? Now, let's say you have a sequence like this, right? Where you have, let's say it's temperature, right? You have these temperature values, x1, x2, x3, x4, x5, and then you want to predict what is the next. You want to predict what is the next temperature, right? Now, if you think about, and then, so this is an example of a sequence, but the sequence problem that we care about a lot these days, can anyone guess what is the sequence problem that we care about these days in all these AI applications? Right, sir? Taylor sequence? Text, right? When we are chatting, we have a sequence. Right, when you do a prompt, you do a prompt, and your prompt is completed, right? So text is what we care about. Next, you might have a sentence like, the student opened there, and you want the model to tell you what is the probable word that comes here. If I'm a human, I can see the student opened there, mouth, book, laptop, notebook, mind, backpack. It can be anything, right? So for a language, so like all these, so basically we are trying to complete this sentence, or kind of getting the next word in the sentence. And once I have the next word, I might predict the word after that. In this case, it might be I predict there is like a full stop, right? But then I start another sentence. That's basically all that happens in ChatGPT or these language models. They are a huge, gigantic language model for predicting the probability of the next word, right? So when we have as input this sequence of words, the language model, mathematically, all it does, it gives you a softmax distribution of the next probable word. That's all it does. That's all ChatGPT is. Nothing more than that. It's just a huge network with lots of parameters to do this next word prediction. So that's, if they ask you in an interview what is ChatGPT, that's what you would say. It's a next word prediction problem. And the output is that softmax probability of all the words in your vocabulary, right? Typically, when you build a language model, you train it on a fixed vocabulary, right? You might, for example, train it on all online novels by a certain writer, or you train it on all of Wikipedia. You have a fixed corpus of text, right? Which means that your vocabulary is also finite, right? So in your vocabulary, you might have, let's say you have this number of words, right? And then what you actually have to build is that you have to kind of give as output what is the probability that this next word will be any one of these words, right? So you would have a softmax over these E words, and that is your output of this model. And then you, when you go ahead.
You're generalizing this, right? You've got to be able to work out this because it could get itself into a corner and not.
Yeah. This is the model, but then you also have to do some sort of path sampling to kind of actually generate it, right?
This
So
is
you
very generalized.
Yeah.
Yeah, okay.
Yeah, but the neural network is kind of, this is the basic neural network, and then you have, I mean, you have like all sorts of stuff like post-training and more variations to that, but this is kind of the basic model here, right? So now, what we can think about is that we have, let's say we want to predict the next word, and the next word is like word at location, my tth word is my next word I need to predict, right? And in general, the way I would think about what is the most relevant word is I need to look at what is the context of this word, right? So I might look at the past k words in my history to figure out what is the next probable word, right? So that's my kind of like something like a context that I'm thinking about. I have a context of these last k words, and somehow based on that I want to predict the next word, right? So mathematically what I want is that my next word WT is going to be a function of my T minus 1, T minus 2 up to, let's say, W, T minus K words, right? So the probability of, so this is what I need to model here. The probability of my next word given all my previous words, I'm going to think of it as a function of all these previous words, and this function I can just use a neural network to model this function, right? Because f is any function, and then we know the MLP is universal approximator, so I should be able to find an MLP that models this function f, right? So how would we, so let's say we right now we don't want to use an RNN, we just want to use an MLP like we know to solve this problem, right? What can we, how can we do this? How can we implement a neural network to solve this problem? So I want to realize this function and build a neural network out of this. What would you, how would you kind of think about designing this architecture? Propagation is going to be for training, right? First we need to define the architecture, right? We have some inputs. We said that the next word is only going to depend on the last keywords, right? Yeah, go ahead.
I'm just thinking the outputs, you would have that many words or that many tokens, and then
Yeah, output is going to be like a probability, softmax probability. That's going to be at the end. Bayesian.
Yeah.
Bayesian is kind of, it's kind of related. There might be a Bayesian, but this, so this is only a probability, which means that at the last year we're going to have a softmax, right? Or the full vocabulary. But we need to start with the inputs, right? So this is like a kind of a context window that is shifting over time, right? But at any given time, I have the last keywords as my input to this network. So I need to somehow pass them into my network and then build a neural network and then get an output, right? Yeah.
So are all those words or tokens, whatever,
Yeah.
passed all together at once when you?
Yeah.
Or are they like processed one at a time?
Right now, if I have the context of last keywords, I want to input all of them together into my network.
Okay.
and then get a prediction, just like a static network. And that's a good point. That's actually why we need something like a recurrent neural network, because that allows us to kind of shift this as much as we want over time, right? But what we can do here is that, so I'm just trying to tell a general process of type of language models. Like, I mean, before we used RNN, and in fact, in some simpler problems, you might just use a simple MLP instead of a RNN. But the way you can think about this is that these like last K tokens, like right now in the modern architectures, we use things like byte-pair encoding, which is much more complicated tokenization strategies. But for this problem, just think of the words as the tokens, and you have a finite vocabulary. But the architecture that you can think about here is like WT-1. This is a word or a string, right? And I can take this and convert it into a one-hot vector, right? How would I do that? So this is a vector of size 3, which is my vocabulary. So basically, I take all my words and index my list of all words in my vocabulary, and I have an array of the same size. So just there is one entry at that index that is 1, and everything else is going to be 0. Right? So this 1 represents the index in the vocabulary of the word WT-1. Right? So similarly, you can do it for WT-2. You get another one-hot vector, and similarly for WT-k, you get a one-hot vector. Right? That's just a vector where you have 1 at the index of the word and everything else is 0. So anytime we do text processing, before we actually submit it to the internet, we also always have to convert it to some sort of vector form, right? We need numbers. If it's an image, you already have these pixel numbers. If it's text, you need to convert it into numbers. So this is your first conversion. And then you can pass it through a matrix. Let's say it's matrix WT-1, and this is matrix, I should not call it W. I want to call it let's call it V, because I have these vectors here. I want to, and then this is VT-2 and VT-k. These are matrices which I multiply to get a kind of an embedding of the vector. So this should give me a let's say it's T. No. Let's call the vector U. Okay. Now for each of the k words in my context, I have k vectors, and the reason I multiply with the matrix, I want to have like a mixed representation. Right? The matrix is going to take all my entries, going to mix them properly, and then I have like a more general representation of the word. And once I have these vectors, right, I can then concatenate all of them to get a huge concatenated vector. And then I pass it through a general MLP. Right? We know how to build an MLP. We're going to have a number of layers. Right? And then I do a softmax over the V values. And that would give me V different numbers for the probability of the different words. So I would have like P1, P2 up to EV. These are all probabilities. So the model tells me, given the last k words, what is the probability that either any of these words, the vocabulary, is the next probable word. And then when I'm actually generating text, I would use this model to get the probabilities, and based on that, I'm going to sample the next word based on the probability. Right? Or I will go ahead.
Well, what is U in this context?
So before I actually build an MLP, I need a vector here. So what I'm doing is that I'm taking each of the words, first converting them into a one-hot vector by just finding their index in the vocabulary array, and then I'm multiplying by these matrices capital V. So each one-hot vector I multiply by a matrix, and I get a more mixed vector, which is likely a better representation of the word.
Okay.
Because it kind of mixes the context of all other words somehow. Right? Now this is a simple matrix multiplication, but in general you might do something like word to vec, if you heard of that. That's a more general way of finding word and meanings, which are more meaningful, but you can do a simple vector matrix multiplication for now. Now, what is a possible disadvantage of this architecture? Like this would solve the problem for fixed context, right? And what can go wrong here? Or why is this architecture not like an optimal architecture? Yeah.
That's a lot of inputs.
Lot of inputs, but you're right. It's about inputs. But yeah, go ahead.
I'm not sure if, well, maybe I'm wrong, but I don't know if it like knows the order of the words.
That's a good point. In general, it's going to be it's going to be independent of the order. But that's a good point. So order is a thing. So if you want to add order, you have to do some sort of positional encoding, right? So we'll see that in the transformer architecture where you need positional encodings. But the other thing is that, let's say I want to build another model where I increase scale, more context. Then I cannot reuse the architecture. I need a different architecture which has basically the number of inputs cannot be variable here. You always have a fixed context size. So if you want to build more context, you have to build another neural network. Or if you want to build language model with a variable context, you have to have a separate neural network for each of your context length size. So those are two reasons why this is not a good architecture, right? So this is where kind of the notion of an RNN comes in. So RNN is for a recurrent neural network. Okay, and the idea of RNN is, so these types of networks were discovered, and including the mechanism of attention, they were all kind of discovered to solve this problem of machine translation, right? You have a long sequence of a long sentence in French, and you want to translate it into English, right? Now, if you're doing this type of translation, right? If you have, let's say, your French sentence has 10 words, 20 words, right? And then your output English sentence might also have 20 words, or plus or minus. I'm not an expert in language translation, but you still, so let's say you have French words like F1, F2 up to F20, right? And then you want to translate into words English in E1 to E20, right? The thing is, when you are let's say you are trying to find out the word E2, right? It's not exactly clear that E2 just depends on F2, right? So E2 might depend on any words in the input French language, like F1 to F20. So the word that you emit at position E2 has to somehow have some sort of accumulated memory or knowledge of all the French words, right? So you kind of need to introduce this notion of memory into the architecture, right? And the memory is, you kind of think of it as some sort of hidden state that you kind of model in your network, right? So what would happen is So this is a general form of a recurrent neural network. So you might have like some initial hidden state, right? And then you pass it through a block, right? So, and this block takes as input, let's say, your first token or input, right? And then from here you compute an updated hidden state, right? And this goes into the next block, and here you have input x2, and at this point you might emit an output y1. Right? So this is the kind of how a recurrent neural network looks like. Okay? So the sequence of H's represent your hidden state. And what is happening is that as you are consuming these tokens, like let's say you're consuming the French words one at a time, every time you see a French word, you use that knowledge to update your hidden state or memory. So this log is kind of keeping memory of all that knowledge that you've seen so far, right? So, and this is going to be a box that has some parameters, like let's say W. It's going to be a parameterized box or function, right? So the way to think about this is, let's say your input here is a previous hidden state, right? So H0 is the previous hidden state, and X1 is the current token, and H1 is the next hidden state. So you're evolving the hidden state. You're updating based on the previous hidden state or memory. So in general, at time ht, it's going to be a function of the previous hidden state and the current input. Okay. So for example, h1 is going to be some function of h0 and x1. h2 is a function of h1 and x2. And ht is going to be a function of ht minus 1 and xt. Okay? And notice here that every time you're using the same function. Right? So basically, if I need to model this with a neural network, I'll be sharing the parameters. Right? And then my output at time t yt is another function g of the current hidden state. Okay? So this is the general form of a recurrent neural network. Why is it called recurrent? Because there is a recursive structure here, right? So f and g are functions, so I can do a neural network to implement f and g. So what I can do is I can say that my ht depends on the previous hidden state ht minus 1. So I'll just multiply by matrix w ht minus 1, and it also depends on the current input. So I'm going to do another matrix v and multiply by xt, right? And then let's say I pass it through a nonlinearity tan of h. Okay, so that's my model of my how my hidden state evolves. So over time, as I get new and new tokens or input words, I'm gradually updating my hidden state with this mathematical operation. So if like t goes to 100, then it has knowledge of all the last 100 words that I've seen so far, right? So I'm capturing it this way, and then my g is my output. So this is like what I'm outputting at every stage. So this g could be a function like another tan h of another matrix u of my current state ht. Okay. Now in this form, this is basically a neural network, right? At every state, I have a xt goes into my network. I multiply by v, ht minus 1 multiplied by w, and then I pass it to a nonlinearity. Right? So you have the sequence of these neural network blocks, and at every stage, so t is variable, t is varying, but my parameters w, u, and v at every stage are same. So we have parameter sharing just like CNNs. So this is also efficient in that sense. Okay. So now with this architecture, we can solve the language translation problem. What I would do, I have my input words. So I have F0. F0 is my first token. So it goes into my block. And then I have H0, right? And then H1, and then I read in F1, and this gives me H2. And if let's say I have 20 French words, so F20, and then I have the hidden state H20, right? Now H20 is a kind of a lump sum of memory that knows all about the 20 French words. It has all the context. It also kind of maintains sort of a temporal sequence here, right? Because the time is relevant here, right? When I add up all the knowledge, I have an accumulated knowledge, and here we can also actually add a positional index to kind of keep track of the time, but that's not important. But finally, this hidden state H20 has the combined knowledge of the whole syntax of the French sentence. And now I have all this knowledge, and now, so this part of it is called what we call an encoder. We are encoding our knowledge of French sentence into a final memory state, which is H20. And now from H20, I'm going to decode or sample my corresponding English output, right? So at this point, I'm going to run it through another block, and then I'm going to emit my first predicted. Based on the global knowledge of the French sentence, I'm going to predict what is going to be the first word in English, right? And then, so let's say I know that my English translation also is going to have 20 words. So if I just emit one word, that is not enough. I then need to emit the next word, right? So what will I do? If I want to emit the next word, right? First of all, the current hidden state H20, I can pass it on as the memory in this decoder block, right? And I can also pass it on over here as the input. And then once I have the first predicted word, I need to know the next predicted word. So I'm going to do is that I'm going to say, I've already generated the first English word. I'm going to pass it on as the next input, right? And then use it to predict the second word, right? And then I keep aggregating the memory into the network. So this is like H21. And now this goes through another block where I'm going to, this goes into as input here, and I'm going to emit E3 and so on until I stop at, let's say, E20, right? And this part is like the decoder architecture. So the decoder is like both. We have basically we have an RNN for encoding the French sentence into a full representation of the French sentence. All the underlying knowledge of French is there in that sentence, and then from that I'm gradually decoding the English sentence one by one, right? So the decoder is also another RNN. So we have an encoder RNN and a decoder RNN. Okay. Now, so this is very good. This is a good architecture. Now the question is, like, why do we need attention or transformers if this works well? So there must be some drawbacks of this architecture. Yeah.
Is it possibly like you lose like grammar structures and like ordering and all that sort of stuff?
Ordering you can lose, but for ordering you can add like a positional encoding, right? You can add an additional input to every block, saying this is block 1, block 2, or something like that. You can add an index there, and that maintains the positional encoding. But one big problem is if you want to, like, let's say translate a kind of a huge text, right? You might have, let's say, 1,000 or like 10,000 long sequence of text, right? What happens is that as you keep propagating forward, kind of when it's time for you to decode, the impact of the words that are really early on in your sequence get diminished significantly, right? That's one problem. The other problem is this is a sequential computation, right? You can only compute, let's say, the hidden state of H20 after you've computed H0 to H19. So it takes a long time for you to actually reach the state once you can start decoding. So depending on how long your input sequence is, it's going to take a lot of time for you to like process the information. So that's where kind of the attention mechanism comes in. What attention does is it frees up the sequential structure and allows you to kind of compute a representation of every block independently and use them and use that in your prediction, right? So the idea is, let's do an example of attention, right? So the type of attention that we see in language models is called self-attention, right? But in general, attention doesn't have to be self-attention. So just to give an example quickly before we give the language example, let's say I have an image, right? And I've broken up it into chunks, right? And then I pass it through a convolution, right? And with a convolutional architecture, right, I have like a representation for every chunk, right? I might have like these values, like C1, C2, C3. I have these convolution values, right? And now let's say, for example, in one of these chunks, I have like a square as an image, right? And then let's say I'm asking a question about this image, right? I'm asking a question like what is the color of the cube? Okay. So like there are other stuff in the image, like whatever, there are other images, but there is only this one block where you have a cube, right? So if you're asking this question, right, you want to localize like which part of the image this question is relevant to, right? So if you think about, like, you can encode this question into like a vector, right? What you can do is that this you can pass it through a RNN, right? And that gives you like a vector that represents the hidden state of the RNN, but that kind of encodes this question to you, right? So let's call this a Q vector. So we get a Q vector, which is a question vector, right? And now every patch in this image, we can encode, like for example, we can encode this patch and get an encoding of a value that represents the hidden state of this patch, and then I can encode a key, right? So what I would do is I would take that patch and multiply by 2 matrices to get a V vector and a K vector. And I do this for every patch. And now what I want to do is that I want to ask which patch is most relevant for this question. The question I encoded as a Q vector, and I have created a key vector for every patch. So one thing I can do to find out which patch is most relevant is I can try to find a similarity between this question vector and the key vectors for all of the patches. I do a cosine similarity or a kind of a vector dot product, and that tells me which one is more important. So most likely, for all of these patches, the dot product between Q and K is going to be low, because this represents a cube object, and the cube is only in that particular patch. So that patch is likely going to give you a high value, right? So what you're doing is you're trying to find out, you're kind of trying to pinpoint some sort of attention structure where you're attending to just this patch using this similarity structure, right? So you can think of each of these patches as like you've tokenized your image into patches, and every patch has some sort of importance, and you're trying to find your question, which patch is more important, by using these vectors. So that's kind of the idea of attention, but here the question is coming from a different modality or different object. My domain object is my image, and I'm trying to answer a question about my image object, but my question is coming from a text prompt. When we say we do self-attention, my question and my objects all come from the same domain. It's all text. That's why it's called self-attention. Okay? So there are going to be 3 vectors that are important here: K, Q, and V. So that was a general attention mechanism. Now let's look at self-attention. So this means that I'm going to ask a question, and I'm going to ask the question about the same object, in this case the language object, or a kind of a text sentence, right? So how would this work? So I'm going to have like this question, and I want to find out where is the next word, right? So what I'm going to do is that, so if I were doing an RNN, right, what I would kind of have these hidden blocks for every word, right? This B word goes into the first block, and then after my hidden state, and that goes into the second block, and so on. But now I want to do this in parallel. So what I'm going to do is I'm going to take each of these words, right? And then I'm going to map each of these into 3 vectors, right? So I'm going to have 3 vectors here. There is going to be a V1 vector, K1 vector, and Q1 vector. Okay? How do we get the vectors? I can just take the word and find the one-hot encoding, and then multiply 3 matrices to get the word. So let's say my O1 is my one-hot vector. Right? And then what I do is that I get V1 by doing a multiplying a matrix by O1. K1 gets a matrix K by O1, and Q1 is a matrix Q by the encoding O1. Okay, and then I do the same for all of these. Here I get a vector V2, a vector Q2, a vector Q2. Okay, so I'm going to build these what are called key, query, and value vectors for every token in my sequence in parallel. That's the big thing about attention. That's why attention works. or is scalable. I can do these computations all in parallel. There is no temporal sequence here. And then here I'm going to do, let's say, V3, K3, Q3, and here is going to be V4, K4, and Q4. Okay. And now, why am I building these representations? Right. So let's say I want to understand this word there, right? So I want to understand what does this there represent, or like what does it refer to? So it might refer to some very earlier token in my sentence, right? So it's not just the case that this there is always relevant to the last 3 tokens. They might have less value here, but there might be a really distant token in the past which is more important. So what I'm trying to model is that I want to ask a question about the relevance of there. The question is encoded as Q4. And if I want to find what other words in the whole sequence is relevant to this, I can use that question to look up the values for all these words. So what I'm going to do is that for all of these words, right? So my question is Q4, right? To ask the question Q4, I want to find out Q4, how much relevance does it have to any other word in the sequence, right? So the relevance is going to be relevance of Q4 with, let's say, with the first word, in this case, let's say the, is going to be the dot product between Q4 and K1. Okay, so the K1 vector of any word tells us I can dot product the key vector with any question to find out the relevance of a particular word with any other word, right? So what I'm going to build up is basically I'm going to take all keys for question Q4 or this there object. I want to compute an attention score for all of these words, and my attention score is going to compute like this. I'm going to take the question Q4 and dot product it with all possible word key vectors. So Q4 K1, Q4 K2, Q4 K3, Q4 K4. I'm also going to do dot product with myself, doesn't matter, right? And then I have these, so this like for example represents like how relevant is the word 3 for word 4, right? And then I have all these scores, and then what I'm going to do, I'm going to do a softmax, right? I'm going to do a softmax of all these go through a softmax, and then I get a score Si is going to be e to the power Q4 with Ki by summation of e to the power Q4 with Kj, where j runs through the full sequence of words. Okay, and now I have a score a similarity score SI for how much does the fourth word, what is the relevance of any word with the fourth word Q4? I have this probability distribution, and now finally I can consider that as a weight, and I'm going to build an attention score for the fourth word. A4 is going to be the weighted sum of all words with this value SI, and what vector do I use here? See, every word has a Q vector, K vector, and value vector. So the value vector represents the inherent value of the word. And then I've used the question about the word in context with every other word by looking up the key and using it for similarity. And once I have the score, I can now do a weighted combination of all the values. So my final attention score, this is the attention block, is going to be the weighted combination of all the V vectors. Okay, and this is my attention. So from here I get the attention score of that word, and similarly I can build attention score for all words in the sequence in parallel. And this is an attention block. Okay. So the attention block becomes this very complex and nuanced representation of a word. Once you have this attention, you can run through multiple attention blocks by sequence, and you finally get a representation of your words and your language, right? Okay. So these are kind of the well-known equations that you might see online somewhere, the attention equation that you do, and you do this for all questions. You get a score SI for every word, and then you compute the attention for a particular token in your language, in your sequence of tokens. Okay. So here, there are two main computations. Is for every key and query pair, you have to compute this dot product, and you have to do it for, if you have n tokens in a sequence, you have to do this n square computation. So that's called a prefetching stage, where you kind of do this all by all dot product, and then the final stage here is kind of a decoding phase, where you're kind of decoding the attention for the particular word that's in question here. Okay, so these final attention scores are like hidden states in the RNN, but you can compute them in parallel. You don't have to wait sequence by sequence. Okay, and when you have these attention blocks in your network, that network becomes a transformer network, right? So that's a very quick and dirty introduction to attention. Obviously, there is not, you need like maybe at least 4 or 5 classes to cover this in detail, but that's the basic idea of attention. And I'll try to give you some pointers towards more resources to learn about this a bit more. But if you are interviewing for a machine learning engineering job, you need to understand attention and transformers very well. I would recommend you try to implement a basic transformer architecture. If you want to interview anywhere, they will definitely ask this architecture. Okay, I don't have enough time to kind of cover anymore, but I hope I give you a gist of this mechanism. and you should be able to kind of pick up from here, kind of learn more about transformers. So that's a very important, relevant topic these days. Yep. Any questions on this? We don't have much time, so if there are any questions, I can answer them. We just have like 5 minutes, so like I thought I would have a bit more time, but like we can talk about the course in general, or like any feedback or anything, any questions that you have about the class or this field in general. We can talk about it for 5 minutes. Yeah.
I have a specific question about this.
Yeah.
If you add another word, do you have to recalculate all the attention blocks?
No,
Oh.
they're already calculated.
Oh, okay.
That's the beauty of attention. It's parallel.
I see.
You just do the computation for that.
Mm-hmm.
I mean, so your key and query vectors are there, right? What would happen is that for the new word you have the key, query, and value vectors. You compute them, and the previous attentions are all done. For the new attention, you just have to kind of do a dot product with a linear number of key values.
Mm-hmm.
Because for every, your new word will have a question vector. You have the dot product. You have to dot product that with all the previous key vectors, and then compute the new attention score for that word.
Wait,
Yeah.
so is the attention calculated using just all the prior words?
You can, no, attention is all to all. So, for example, in general, attention is all to all. So A3, that's a good point. A3 attention would depend on A4, A2, and everything. But if you want to predict the next word, you cannot look ahead. That would be cheating. So in that case, you have like a, so you have this dot product between a question vector and a key vector. In general, it's all to all. But so it's going to be like a full matrix of these values. But when you want to predict your next word, you just do it like it's going to be you only have like one half filled out. Because when you're computing the attention for A3, right, you have to think that you don't know A4. So just consider the dot product with everything before. So in that case, it's like asymmetric. You just have, you do the computation, you ignore the next word. And then you use A3 to kind of predict your next word. Yeah, good question. Yeah. Yeah.
There was like a recent Google paper like a week ago or something like that about like how non-reasoning transforming LLMs
What reasoning did you say?
like non-reasoning LLMs they
to do based like that, or
Yeah.
where it creates a list now.
but the finding they found was that if you just put the prompt twice it would have an increased accuracy because of the context increase from
Yeah.
applying to the front. Does that mean that they're considering those prompts slowly from start to finish instead of as a whole?
If you're talking about so these language models were meant for doing things like text completion or kind of writing nice text, right? But now these are also being used for mathematical reasoning. How are they able to do analytical reasoning? Is that what you're asking? They're not meant to be formal mathematical systems, but they are able to do that.
Well, what it sounds like from what this sort of thing, it sounds like it should have context of those starting words of the prompt or something because of it's able to consider the prompt as a whole, but that's not what they found. So I wonder if that's
I see.
a flaw in their or like a difference in like how they do the architecture for something like that.
So you said this was a Google paper?
Yeah, it was really recently, like like you can find it just looking up like double prompt.
Yeah, I'll have to take a look at that paper to see.
Yeah. I mean, how does context come into play here? Because obviously expanding context is like probably one of the most important things that you can do right now.
Yeah.
Like I realize this is probably more than you can cover in an hour of lecture.
Yeah. I mean the general idea of context is kind of like how much window you have, like
That would just be included in the attention blocks, right? Essentially.
yeah, like how many attention blocks are you gonna consider for your next word or something like that? At least at the basic level.
But it's also got to have a rear-facing aspect as well as the forward-facing.
What do you mean by rear
Well, because it's, I mean, it's creating a coherent like storyline.
Yeah.
So like obviously there's an end goal that it needs to get to as well, which
Yeah.
is context-based.
Yeah. I mean, there is also these, for limited context, you can also like look at external sources, right? There is things like RAG, retrieval augmented generation, where you have like more longer term context stored in the database. And what you would do is that from your small context, you can like use a query to kind of index into a database to find more longer documents about your context. And then you kind of embed that back into your prompt, and then you get a more richer context to kind of answer your question. So that's one way to deal with like memory context limitation, like where it's like a cache in a computer system. Your cache is limited, but you can always fetch data from memory or disk. So the RAG is like your long-term AI memory. That's one thing to about. Yeah, I'll share a link to some resources on language models. I mean, that would require another course to kind of go into those details. But I think that we have the
Thank you.
Thank you very much. Take care.